Okay, good afternoon, and now I will introduce chapter 15. We don't have too much, I will say, material in chapter 15. We are mainly going to talk about the thermodynamic laws, the zeroth law, the first law, the second law, and I will maybe my focus is gonna be on the first law of thermodynamics. Now, the zeroth law, we don't have actually to maybe worry about. It's a very trivial statement saying about if I have something that is, let's say, object A that is in thermal equilibrium with B, and that B is in thermal equilibrium with another object C, then for sure A is in thermal equilibrium with C. Now, as I said, my focus is going to be the first law of thermodynamics. And the thermodynamics here is telling you that the internal energy of the system and the heat and the work done, they are, like I will say, they are really the same basically thing. What does that mean? That means like I can apply work, and that work is going to be converted into heat or changes in internal energy, or if the heat is removed from the system or added the system, that this is going to make the system capable to do work, or is going to have changes in its internal energy. Now, these are the terms that we are going to use. There are many forms for the first law of thermodynamics, different definitions. For us, we are going to use this one here, where the internal energy is Q minus W. But you need to here take care of what are these. Change in internal energy. Of course, all of these quantities are measured in joules. Delta U, change in internal energy, and that is really the internal energy, the final minus the initial. Q, it is the net heat transfer. Okay, then the net heat means like sometimes the system is going to absorb and the system is going to give off, and then this is really the net. W, in my definition, it is the work done by the system. If we are going to talk about the work done on the system, is going to be negative that. Okay, and this is very important in our definition. Delta U depends on the initial and the final state of the system, and it has nothing to do with the path, like how this was done, but for the work and for the Q, they are really path related. Now, there are several processes here that we are going to maybe talk about. One of them, it is the isothermal process, and the isothermal means iso means equal, and thermal, which means that is a temperature that is going to stay the same, and U, the internal energy of the system, depends on the temperature. Then when T is constant, U is constant, and therefore the change in the internal energy of the system is going to be 0. Now, based on my equation, then I can here go make this 0, then Q equal W. And this is only for isothermal. Now, for isobaric process, isobaric means constant pressure. We can represent it with that PV diagram. The PV diagrams also in this chapter are very important. It's a horizontal line, and always, this is general. The work done is going to be area under the curve. You know, it is actually the, we can say the integral, but for our course, we don't deal with integration or calculus, and therefore, we're going to say that the area under the curve is the one that is representing the work. And now here, this is easy to calculate area, but sometimes you're gonna find that the areas they're gonna be different, and then you need to cut it into areas that you are able to measure and find, like, the calculation for that. Now, also, another formula that we are using for the work done, it is minus P times delta V. Okay, remember B here, it's a constant number, and the volume change is going to be, this is the initial, this is the final. The next process, isochoric, and this is constant volume. And when we have constant volume, this process is going to be a vertical line, and that W is going to be 0 because we don't have an area under the curve. And from that, we can say delta U equals Q minus W. And since W is 0, then the change in the internal energy is going to equal to Q, which is the quantity of heat. Now, another process that we are interested in, it is adiabatic. And in adiabatic, the system is isolated. We added like kind of an insulation for a room, let's say, or any system that we are dealing with. And then Q is going to be 0 because when the system is isolated, no interaction with the environment outside, and therefore delta U is going to equal negative W because Q is 0. Okay, this is one of the questions here. What is the change in internal energy of a car if you put 12 gallons of gasoline into a tank? The energy content of the gasoline, it is 1.3 10 to 8 joules per gallon. All other factors such as the car's temperatures are constant. Now, the energy content of a gallon of gasoline, it is 1.3 10 to 8. And then if I have in that car 12 gallons, then I will say it's going to be 1.3 10 to 8 times 12, and that is going to be 1.6 10 to 9. And here, if we're going to assume that the temperature is going to be 0, the change in the temperature is going to be 0, the isothermal, we are going to have here, they said like that the temperature is constant. Then I will look at the change in the internal energy at 1.6 10 to 9 joules. Now, what is the change in internal energy of a system which does, okay, then now the system, okay, this is work done by the system, and therefore we are going to give it a plus 4.50 10 to the 5 of work, while 310 to 6 joule of heat transfer occurs into the system. Then again, Q is positive. And also we have 810 to 6 joules of heat transfer occurs to the environment. Then the system here, it is gaining in 310 to 6 and losing out negative 810 to 6. Then we need to find the net heat, which is going to be 310 to 6 minus 810 to the 6, and that is going to be negative 510 to the 6. Now delta U equal, of course, Q minus W, and that is Q net, which is negative 510 to the 6 minus 4.5 10 to the 5 joules, and that is going to be negative 5.45 10 to the 6 joules. And therefore, we are going to find that the energy, the internal energy of the system is going to decrease. Okay, most of the time, you're going to have a PV diagram that you are going to use to calculate the network output of a heat engine following a certain path. And here we are going to calculate the network for this object, which is like this process going through A to B to C to A. Now, one of the things that I want you to know that going back to the same state is going to make the change in the internal energy equal 0, since it is the initial equals the final. Also here, the work done is going to be just the area enclosed by this shape. And I can calculate the work as A1, okay, which is going to be, I can say that this is a triangle. All right, like I can make this, dissected into different pieces, A1, A2, and A3. And based on that, I will be able to calculate what is really the total work done by calculating the area under the curve. Now, the second law of thermodynamics, it is talking about a machine that we are going to use, or it's an engine that is gonna have the heat transferred from a reservoir that has a temperature T high, and then is gonna do some work that is my output, and is gonna expel a Q cold. Now, that is really the work done is going to be the difference between the two Q's. And always we are really interested in the efficiency, which is the work done divided by the Q heat. And remember, the work done, it is Q hot minus Q cold divided by Q hot. Then the efficiency can be calculated as 1 minus a Q cold over Q hot. Now, this is really the engine that we are going to find in everyday life, and the efficiency of it, it's really very low. Now, there is a scientist, his name Carnot, was talking about we should there should be a perfect heat engine around me, and that is going to be the Carnot cycle, where it is the most efficient process that is going to be done in a heat engine. And he connected the efficiency now to the temperature instead of the heat. Then the efficiency for Carnot is going to be 1 minus Tc over Th. Here, we are talking about a cyclical heat engine operating between temperatures of 45 and 150, produces 4 megajoules of work on a heat transfer of 5 megajoules into the engine. Okay, then here, W we know it is Q hot minus Q cold. Then I will be able to calculate a Q cold, which is the Q hot minus W, which is going to be 5 megajoules minus 4 megajoules, and that is going to be 1 megajoules. Now we need to calculate the efficiency. It is the work, like this is for a regular engine, like any engine, then it's going to be W divided by Q hot, and that is going to be 400 megajoules divided by 5. Oh, this should be here. I'm sorry, this is not 500. This is 4. Only 4. I barely, like with my glasses, I can see the decimal. This is 4.00 megajoules divided by 5 megajoules, and that is going to be 0.8. Now, okay, for that efficiency, if we calculate that in temperature, then you are going to find that is going to be of course, kelvins here, 300 kelvins divided by 723 kelvins, and that is 0.15. That is not correct. This is not a reasonable example, since like Carnot always should be more efficiency than the regular heat engine. Here we have another example talking about how much heat transfer occurs to the environment by an electrical power station that uses 1.25 10 to 14 joules of heat transfer into the engine with an efficiency of 42.0%. I know that the efficiency is 1 minus QC over Q hot, and then Q cold equals 1 minus efficiency times Q hot. I will convert the percent into decimal, then it's going to be 1 minus 0.42 and then multiply by the amount of heat, and that is going to be 7.25 10 to 13 joules. Now, what is the ratio of heat transfer to the environment to the work output? Okay, we can say QC over W, and that is QC divided by Q hot minus QC, and that is going to be 1.38. The last part, C, is how much work is done. We said we can calculate the work that is the difference between a Q hot and Q cold, and that is going to be 5.25 10 to 13 joules. Another problem here, a certain gasoline engine has an efficiency of 30%. Look at the, the efficiency, it is low. What would the hot reservoir temperature be for the Carnot engine being having that efficiency if it operates with a cold reservoir temperature of 200? Then the temperatures are given to us. Then I will say, no, not the two temperatures. The cold is given to us, and we have the efficiency. Then we will be able to calculate the hot one. Okay, now E efficiency, it is 1 minus TC over TH, and that is TH equals TC over 1 minus efficiency, and you will say 473 Kelvin divided by 1 minus 0.3, which is the efficiency converted into decimal, and that is going to give us 676 kelvins, which is 4.03 degrees Celsius. Now, other pumps or heat engines, or like something like the heat engines, we call them heat pumps, and refrigerators like the AC devices and refrigerators. These are really compressing cold air and is doing heat, to like expelling the heat, and it will not violate the conservation principle of energy. But here we will not talk about efficiency. We are talking about what is called coefficient of performance, COP. Okay, and that is going to be for heat pump, and that is a Q hot divided by W. A refrigerator, it's a heat pump, and it takes warm ambient air and expands it to chill it, to make it colder. Okay, now what is the coefficient of performance of an ideal heat pump that has heat transfer from a cold temperature of -25 to a hot temperature of 40? Now, COP for a heat pump is going to be 1 over the efficiency, which is T hot divided by T hot minus T temperature, and that is going to be 313 Kelvin divided by 313 Kelvin minus 248 Kelvin, and that is going to be 4.82, and that is the number for the coefficient of performance of a fridge. Now, show that the coefficients of performance of refrigerators and heat pumps are related to a coefficient of performance of refrigerator equals the coefficient of heat pump minus 1. And we can actually start with the definition. Q hot minus QC equals W. And then we divide W on like the equation, all the terms. Then it's going to be Q hot divided by W minus QC divided by W equals 1. We know that the coefficient of performance for a heat pump is Q hot over W, and the coefficient of refrigerator Q cold divided by W. And then therefore we can say the coefficient of performance of a heat pump minus the coefficient of performance of a refrigerator equals 1. And therefore, we can say that the coefficient of performance of a refrigerator, it is the coefficient of heat pump minus 1. The last thing that we are going to talk in this chapter, it is about entropy. And I will say entropy, it is related to the chaos in the system, or the what is called the disorder. And we can also say it's the loss of energy available to do work. And the laws of the second law of thermodynamics, it has so many statements. One of them is like, I cannot have an engine that has 100% efficiency. And the second law also has another statement that is saying that the total entropy of a system either increases or remains constant, and it never decreases. We can find the change in entropy as Q divided by T, and here of course T should be in kelvins. On a hot summer day, 410 to the 6 joules of heat transfer into a bar car takes place, increasing its temperature from 35 to 45 degrees Celsius. What is the increase in entropy of the car due to this heat transfer? Actually, we can just divide Q by the temperature. And here there is a mistake. That should be in kelvins. Okay, the heat, the temperature. The heat, it is 410 to the 6 joules, and this is divided by 313, and this is Kelvin. And the answer is going to be 1.28 10 to the 4 joules per Kelvin. Okay, that's for chapter 15. Thank you, and see you soon.